Hello everyone. I think remember in the last session we end with the air cooled and water cooled chiller, nothing but the chill water system. We have some more topics to discuss in chapter 5 to conclude this chapter 5. So in this session, first let me continue with the topic DX and chill water system. You see, already we discussed the different types of DX system and the chill water system, but you can consider like a summary for this two system in this DX and chill water system. After that, we have a topic for this district cooling system and the radiant cooling system. Okay, district cooling system is similar like chill water system, but instead of supplying the water from the chiller, you'll get from the district cooling plant. I'll show you. And in radiant cooling, the concept of cooling is using radiant panels, which can be in the floor or which can be on the wall or in the ceiling, etc. And in that also you'll find the supply of chill water. Okay, so if you just classify this radiant cooling or district cooling and chill water chillers, all comes under this chill water system category. And you know this split window, ductable split package, including VRF, that we can consider as a DX system. So first, the first topic of today's session is the same DX and chill water system. Just for conclusion, or we can say this will help you again to take the decision at the time of selecting the system. You know this is just for confirmation. You can verify all these points, what we discussed till now for DX and chill water system. So let me share the screen. You can read on screen. In short, we used to call DX, it's a direct expansion system. And the second is a chill water system. So you know this, just let me read and you'll get the confirmation. The difference between the two systems, DX and chill water, is in DX system, the refrigerant is directly responsible to cool the air. And in chill water system, the refrigerant is used to cool the water. Then water is responsible to cool the air, like what we discussed in the previous session. That is a major difference. Apart from this, installation point of view, efficiency point of view, or cost point of view, we have these differences that I'm going to cover in this. So you already know the working principle, what I explained. In DX system, the cooling process involves the direct circulation of refrigerant between the indoor and outdoor. The refrigerant evaporation in the indoor evaporative coil and to cool the indoor air and then return to the condensing unit. You know this if you talk about DX, but if in chill water system, first we are going to cool the water, then the water is responsible to cool the air inside the AHU or FCU. Okay, and the hot water return back to the chiller, or we can say chill water return. Generally, we are not calling hot water return. We are calling chill water supply and chill water return because the temperature difference is 10 degree Fahrenheit standard in between the inlet and outlet to the chiller and inlet and outlet to the AHU. These technical points we'll discuss at the time of chill water pipe sizing and the selection part for the chiller. Next, the components, you know this. In DX system, condensing unit, you know what are the components in condensing unit. Evaporative coil in the indoor unit and the refrigerant line. What we discuss in detail, this is just a summary. Similarly, in chill water system, water circulates to the system. You'll find the separate water loop, nothing but chill water loop, nothing but secondary system. You know, you'll find the AHU, FCU, and the cooling tower for water cooled chiller, what we discussed in the previous session. Apart from this, you'll find the pumps, valves, control, etc. Valve means that comes under pipe accessories. We have a separate detailed topic for this pipe accessories, which is very, very important for interview point of view. As a design engineer or as a site engineer, we have a topic that we'll discuss at the time of before pump selection with the detailed drawings. Next, application for DX system, you know, we can use for the small commercial space or means for residential mostly, or small commercial spaces and light commercial, and suitable for simplicity in installation and the cost effectiveness. Means I'm talking about the initial cost. Now if you compare with the chiller, you see preferred for large commercial and industrial application, what we discussed in the previous session, also for high-rise building or commercial. It can be a residential apartment also, but if it is a high-rise building, we are using the chill water system, industrial application or commercial, etc. And for multiple zoning, and can be used for both cooling and heating with a single AHU, but no doubt we require a separate boiler for that. Okay. Next, efficiency point of view. You see, this efficiency point of view, we cannot say always the chill water is best or the refrigerant means DX system is best. Depends on the other parameter also. You see, in general, if you talk about or if you compare this chill water and DX system, The DX system, the efficiency is slightly lower compared with the chill water system. But you see, for smaller application, this is a good option compared with the chill water, because in chill water, the initial cost is going to be high. But chill water is the best option in terms of efficiency point of view for large project, because we're using water to circulate. We're using the chill water for circulation instead of supplying the refrigerant. So it's going to be the efficient option, and can be used for multiple zones and for number of floors compared with that DX system, because we have some limitation in the DX system. Even in VRF we have 50, 42 or 50 TR one outdoor. No doubt in that we can achieve say 300, 400 TR with a multiple our VRF outdoors, again, which will connect to the n number of indoor. But instead of that, we can go for chill water system, especially for the running cost point of view. And based on the application also, for example, if the usage is limited, then we'll not go for the chill water system. So even for a big project, one can deal with a VRF or multiple DX system if the usage is limited. Suppose throughout the year, if you're using for 2 or 3 months, then we'll not think for the chiller, because the initial cost is going to be high. And the saving in 3 months is not considerable, no, compared with the means instead of increasing the initial cost. If the usage is more, then the chill water is a good option, because if the usage is say 6 to 8 months throughout the year, so monthly saving, that is considerable, and that will help you to get the recovery in the payback period. And after that, you can expect this saving in initial cost, sorry, saving in running cost. So we have a number of parameters. Now, if you talk about installation for DX system, installation is not complicated compared with the chill water system. In chill water system, separate primary system, separate secondary pumps, and a complete pipe network with insulation, and enough space is required for chillers. It can be air cooled chiller, or if it is a water cooled chiller, we require a separate space in plant room and separate space for this cooling tower, etc. So installation point of view, this chill water system is complex compared with the DX system. This all just is a confirmation. So this is some important points related to DX and chill water system. Next, we have two more system to cover this chapter 5. Not two more, we have this CAV, VAV and dual duct also. Let me proceed with the district cooling system. This is interesting. And if you talk about say Dubai or Qatar, or even in Saudi, even in India, not in all the location, in some locations, you can find this district cooling system. So the concept of district cooling system is it's a chill water system only, what we discussed in the previous session. But you see, centralized cooling infrastructure means away from the building, you'll find a cooling system, a district cooling system with a high capacity. And in that, you'll find mostly absorption chillers, and which is used to produce a chill water. And the chill water through insulated pipe we can supply to multiple buildings. For example, you can find this in image. You see, assume that this is a chiller plant, a district cooling plant, and this plant is producing say thousands of chill water GPM, and this chill water through this pipe network, which is underground, like a municipal water line or other lines, with the insulation, which is this chill water is going to supply to the building. For example, building 1, building 2, building 3, or it can be residential, it can be commercial, it can be industrial. And you can find the return also. You see, supply return. You can compare similar like a chill water system. But the point is, the chiller is not in the building, it's away from the building, and the capacity is high, which can serve multiple buildings. So the chill water with insulated pipe, we are supplying to multiple buildings. And inside the building, you'll find FCU and HU as per the capacity requirement for the particular space or for the floor. And apart from this, when this pipe is entering in the building, it will enter in a separate BTU room or BTU meter room. BTU meter we used to call, what is BTU? BTU thermal unit. So the name of that meter is a BTU meter. Like when we get the municipal water supply line in our home or the building, that is going to connect it to the water meter, which is used to pay the monthly bill according to the consumption of water. Similarly, when the chill water is entering in the building, first it will connect to the BTU meter, and as per the requirement of the building, for example, it's a multi-tenant building, or assume that this building is a residential building and with n number of flats, and each flat have means the owner of each flat is different. Multi-owner buildings means multi-flat owner buildings. So everyone is going to pay the bill according to the usage. So in that case, for each flat, you'll find one BTU meter. So according to the consumption of chill water, means energy, not they are not consuming the water, because you see you'll find the return line also. So circulation of water, but the energy is going to use the cooling effect. So according to that, the building owner or the flat owner is going to pay the bill. I'll show you one drawing, you'll get the clear idea. Just at this level, I'm just giving the concept. So very simple
Just
concept.
just one
Same like
question.
1 minute. Same like chill water system, but only the difference is the chill water is not in the building. Sorry, the chiller is not in the building. The chiller is away from the building, and chill water is supplied through the insulated pipe to the different building, and the building owner is going to pay according to the usage, which you can find in the BTU meter. And the usage is energy usage, not means the cooling effect, not the water consumption. Yes, online.
So every apartments there will be BTU meter. For example, this is a society building or residential building. So that BTU will means measures the cooling effect. I can say that, not the electricity on neither the water consumption, right?
Yes, the energy consumption. Now, so let me play a video. You'll get the clear concept of what this district cooling system. So please have a look. So I think you got the idea. And we have some advantage and disadvantage also. The advantage is saving in the running costs, saving in water, saving in the environment. But the disadvantage is initial cost is high. And a single building owner cannot afford this. It can be a separate supplier or from the authority of that particular area. And this is also one type of chill water system compared with the DX system. Okay, and let me show you some drawings. You see, first of all, these are detailed drawing for the BTU meter. One example, before supplying the chill water to a apartment or to a floor or to a building. Suppose if it is a one owner building, you will find 1 BTU. Or else if it is a multi-owner building, so each flat or each floor have its own BTU meter. So this is a chill water supply and these are written, and you can find the BTU meter. This is similar like a water meter or any other meter, which is used to read the information according to the consumption of the cooling effect, not the supply of water. Similarly, this drawing will help you. And this supply of water from the district cooling is from outside the building. No? So this pipe you can find in the site development plan. This I'm showing the preview. This pipe, this is a site development plan. In this, you see the pipe is entering in the building. This is from the district cooling plant, or else detail of BTU room. In that you'll find n number of BTU meters. Like you'll find electrical room. In that you'll find the multiple electrical meters as per the apartment. Similarly, you'll find the BTU meter, and you see this is schematic, the supply of chill water from the cooling provider. Then it will connect to, you see this is a secondary pumps, and it will enter into the different floors. You see, entering the floor, and it's a BTU meter, 10 number of BTU meter. Assume that in this floor there are say 10 flats, so all 10 BTU meters and the supply to each and every flat. This is just for example. At this level you may not get the complete detail for this. At the time when we talk about the chill water system, you will get more idea about this primary details, secondary details and all this, and the same you can consider for the district cooling system also, except the chiller. So this is just a preview. Next, we have one more system, radiant cooling. This is not commonly used, but this also a system in market. Even
For district cooling, I can say that in universities, some big universities, the system is applicable, right?
you see, even in India also it's available. Or if you have blocks of building, in that also you may find the district cooling, a separate cooling plant for a number of buildings for that particular community, for means particular infrastructure, for a particular means for the same builders. They
Mhm.
may you may provide a separate district cooling. So this concept you'll find even in India also, and commonly in Qatar, Dubai, or in many areas. Next, we have a radiant cooling. You see, this also a system you can consider under the chill water system, not a DX, and not commonly used, but in some project you'll find this one. The concept of radiant cooling is we are supplying the chill water in multiple pipes, which is going to be below the floor or in the wall or in the ceiling, a small PEX pipes in which we are supplying the chill water, so that we are restricting the heat transfer through this building structure inside the building. That is a concept. And we are calling radiant cooling because you are using the radiant panel in the floor, and the heat is going to be through the radiation, means electromagnetic waves. Nothing but you see, all these bodies will provide this electromagnetic waves. Now, even the human body also emit the electromagnetic waves, means radiation. So the simple concept, but initial cost in this is high because at the time, and this can be done at the construction stage only. After that, we cannot provide because we are going to lay the pipe before the flooring. I'll show you. I'll play one video. You'll get the clear idea. But this also comes under chill water system. But this is not like a conventional type. This is somewhat different. Okay, compare with the chill water system or district cooling system. So how exactly? This video will help you. This is a bit lengthy. Just have a look. You'll get the concept. At this level, just I'm providing the concept.
Most current systems provide cooling by air. However, water can be an alternative to air in a lot of applications. Let's see how air compares with water as a cooling medium. Water is 832 times denser than air and has approximately 4 times the heat capacity as air. Effectively, one must circulate 3,300 liters of air as opposed to 1 liter of water to absorb the same amount of heat. Sample this. To provide 100 TR or tons of refrigeration worth of cooling, one would need 40,000 CFM of air compared to just 32 CFM of water. Moreover, the air-cooled system would need 6 times more power than the water-cooled system for just pumping.
And you see, this comparison is applicable only for extracting the heat, not for circulating the air. Again, for in air conditioning, we required the supply of air also, including the fresh air. Only maintaining the temperature is not enough. You need to maintain the movement of air as well as the required fresh air. So in the radiant cooling system, we required a separate system to provide the fresh air also.
Clearly, water is a much more potent cooling medium, and cooling by water is more efficient than cooling by air. Radiation, or radiative heat transfer, is what occurs when heat radiated from one body is absorbed by another. We feel warmer around a fireplace because of the heat radiated from the fireplace to our body. Mean radiant temperature and perceived air temperature. One of the fundamental properties of heat transfer is that heat flows from a hotter body to a cooler body. In any room, there is constant heat exchange between the walls, roof, floor, people, and other objects. The weighted average of the temperatures at which the surfaces of all such objects in a room radiate heat is the mean radiant temperature. Mean radiant temperature quantifies the influence of surface temperatures on human comfort. For example, a hot roof, windows exposed to direct sunlight, etc., will increase the mean radiant temperature. The higher the mean radiant temperature, the cooler the air required to achieve thermal comfort. On the other hand, if the mean radiant temperature is lower, occupants can feel comfortable at relatively higher air or space temperatures. One of the ways of achieving efficient and sustainable cooling is therefore through a system that lowers the mean radiant temperature, which will reduce the amount of energy required to provide thermal comfort. Panels. In radiant panel type cooling, copper tubes may be used for circulating chilled water. Piping. Loops of cross-linked polyethylene pipes.
You see, copper tube means which is used to cool the water, not below the floor. Below the floor, you'll find the PEX pipe, polyethylene pipes, not the copper pipe, because that is going to be very expensive. In the previous part of this video, he's talking about the copper pipe, which is used to cool the water, like saline tube evaporator.
Are embedded in walls, floors, ceilings, and chilled water is passed through them. Control system. Along with the switching controls, these controls may also be used to regulate conditions using inputs from various sensors. Chiller. A chiller is used to cool the fluid medium to required temperatures.
You see, in the chill water system, the chill water we are supplying to AHU and FCU, and AHU and FCU is supplying the cool air. But here also we are using the chiller with manifolds. Manifold means a number of pipes will connect to the main pipe, and through which we are supplying the chill water, and the chill water is below the flow level. We are not supplying the chill water to the AHU or FCU.
Other components like manifolds, valves.
You see, like you can consider this as a header, and you can connect this PEX pipe to all this. It can be 4, 5, 10, depends as per the requirement.
Pumps, etc., complete the layout. Chilled water from the chiller goes to the manifolds and is distributed through the grid of pipes installed in the room. The chilled water in the pipes then absorbs heat from the ceiling or the floor, making it cooler than the objects and the occupants in the room. The resultant temperature difference ensures that heat from the bodies is now radiated towards the cooler building components, leading to a sensation of thermal comfort. Radiant floor cooling. As the name suggests, pipes embedded under the floor cool the space above in this layout. Radiant ceiling cooling. Installed directly below a structural ceiling, panels with embedded pipes or pipes attached to the ceiling and covered with plaster. Radiant wall cooling. Small diameter pipes are attached to walls, then plastered over, or panels with embedded pipes are mounted on the walls to achieve radiant wall cooling. Pipes may be run from the floor as a same circuit, or a distinct circuit can be installed. Latent heat load management using a dedicated outdoor air system. Comfort is as much about humidity as it is about heat. While radiant panels take care of the heat in the air, a dedicated outdoor air system is essential to handle humidity in the space.
Humidity as well as the pressure requirement.
Along with dehumidification, the dedicated outdoor air system accomplishes ventilation and filtration. The air quantity requirement in this system is much lesser when compared to a typical air-based cooling system. Together with a dedicated outdoor air system, radiant cooling can completely address the thermal comfort requirements in any climatic zone. Using heat exchangers in the form of chilled water carrying pipes embedded in floors or walls or ceilings or in panels ensures the availability of a much larger area for heat exchange compared to a regular heat exchanger, which is impeded by space constraints.
One more point here, you see, the delta T is not much in this compared with the chillers. You see 20 degrees centigrade, 15 degrees, 5 degree is the difference, delta T.
Sufficient cooling can be achieved with higher chiller operating temperatures, which in turn results in a higher coefficient of performance for the chiller and consequently lesser energy consumption. A room with a regular air-based cooling system has a higher mean radiant temperature and therefore needs a low room air temperature to make the occupants feel comfortable. A radiant cooled room, however, has a lower mean radiant temperature and can provide the same cooling effect at a relatively higher room air temperature. In radiant cooling systems, which have a dedicated outdoor air system as well, the air requirement is considerably lesser than a regular air conditioner, which is also reflected in the reduced power consumption of the overall system.
You see, if you compare this overall with the chilled water system, this you can consider a good option, but the initial cost is high. No doubt, running cost is less compared with the chill water system, but at the same time, we required this radiant cooling. It's a one-time investment initially, but in terms of running cost, running the chiller with the pump, but compared with the chill water system, we don't require very low temperatures like chill water. In chill water, the supply temperature, you'll find 6 to 7 degrees centigrade. In this, we required say 15 to 17 degrees centigrade. So because of that, power consumption in chilled water is less, and the air requirement also reduces because of this main radiant temperature. So overall, if you compare, this running cost of this radiant cooling is less compared with the chilled water system, but at the same time, initial cost is high. I need to take the decision at the construction stage only, so that one can complete this piping and all at the time of construction. Okay, so these are some points related to the radiant cooling system. I add this because this also a system in the market, not commonly used, but this also you can find in HAP software or else even in Revit software, you'll find this in the system list. Okay, so use in some project, not in all the project, generally for the big project, not for the small project. So let me continue with the all air conditioning system. The topic is all air conditioning system, and all air conditioning system, it not mean that it's a separate system. All air conditioning system, it can be a part of DX system or it can be a part of the chill water system. In DX system, the air we are going to cool means the air loses the heat directly to the refrigerant, in DX system, right? And in chill water system, the air loses the heat to the chill water. So you'll get the cool air from DX system as well as in chill water system, and you know the difference between the two systems. But now, after getting the cool air from the AHU, how you're going to handle that air? For that, we have this all air conditioning system. It means in the background of all air conditioning system, the cooling effect either with the DX system or with the chill water system. It's not a separate system. It's a part of, it can be a part of DX or chill water system. Now, after getting the cool air from the AHU, how we are going to handle that air? So for that, we have three options. First is a CAV. Second is a VAV, and third is a dual duct. And CAV is not new. You're already aware of that. So in short, we used to call CAV. It's a constant air volume variable temperature system. Once again, you see, constant air volume variable temperature system. It means the default system, what you already know. I think you already update DX or means ductable split in chapter 5. If you talk about this ductable split, which I cover in chapter to the AHU, we are going to connect the duct, and the duct will supply the air to one space or to multiple space. And whenever you switch on that AHU, switch on that unit, all the time through the A terminal. A terminal means it can be a diffuser, it can be grill. The flow rate of air is going to be constant. So it means the normal system. The default system is a CAV. You see, constant air volume. Whenever you switch on the unit through the duct, the air will supply finally through the A terminal. For example, if I design this room for say 800 CFM. So whenever I switch on the unit, all the time the flow rate of air is going to be same, that is 800 CFM. And beside room, suppose as per the load, I designed for suppose 500 CFM, and one more room say 700 CFM. So and all this space is connected with one unit, so one AHU. So when I switch on that unit, that ductable split, or it can be AHU connected to the chill water, whatever. So the flow rate of air from the 8 terminal is going to be same, means the normal system. That's the reason we used to call constant air volume. And why we are calling variable temperature system? Because the thermostat connected to the AHU, through which I can increase or decrease the temperature, right? It is possible, na? But the flow rate of air is going to be same all the time. Whenever the machine is operating, whenever the machine is on, means AHU is on, the flow rate of air through the A terminal is going to be same, what you design for, like normal system. But the temperature you can increase or decrease with the thermostat. So the default system, what you already know, that like ductable split or chill water system with the AHU, normal AHU, is a CAV. And CAV system we can also call as single zone. Why single zone? But before this, do you know the difference between space and zone online? If you don't know, please make a note. I think we discussed this, but one more time, this is a right time to discuss in detail. So please make a note. Space refers to closed boundary regions. In general, we used to call room. Room nothing but a space. Technically, we used to call space. In architecture side, we can call room, but technically for mechanical electrical, we used to call spaces. So space refers to a closed boundary region. Next point, you can write zone. Zone refers to thermostat. Thermostat means what? In bracket, controlling. I'll explain. We have different possible cases for the zone. Here on screen, for example, here case 1. In this room, I'm going to install one split unit with outdoor. So this is space 1, and for one space, one unit. So this is what? Zone 1, means one space, one unit. Because for this split unit, separate controlling, separate thermostat remote is there. No? This is one case. First case. Second case, for example, say multiple spaces. To all the spaces, I'm going to supply the air with this AHU, and I'm connecting the duct. Through the duct, air is going to supply through the diffusers. These are the branches and say diffusers. So how many spaces in this case? 1, 2, 3, 4, 5, 6. So spaces are 6. Here space is one number only and zone also 1. Here number of spaces 6, but number of zone is only 1. Why? Because only one controlling through this thermostat, na? And you can consider this like a CAV system, and whenever you switch on the unit, you'll get the flow rate from this diffuser as per the design. It will not decrease or increase, the same flow rate. So it's a CAV system, and CAV system we can call as single zone, because you see for all the spaces the AH is 1, so it's a single zone. So this also an example for the zone. So zone, don't think that zone is always a set of spaces. It can be one space, one zone, or multiple space, one zone. Okay, or it can be the mix of both. For example, consider this 6 spaces again. This 4 spaces I'm going to supply with this unit, but this for this 2 spaces I'm going to use separate split. So how many spaces? Spaces 6, but how many zones? 3 zones, right? So I think you got the clear idea about the zone, right? And also about the CAV system. Now the question is how to... Yes, online.
Okay, sorry. What about just like I'm just a little bit confused with the thermostat. The term thermostat, with whether we is it the same whether we use like a VRF system has in each room you just give it.
VRF is different. VRF is different. Here I'm talking about, you see, VRF means one outdoor, multiple indoors, which I cover in chapter 5. So in that case, one outdoor unit, but connected with the multiple indoors, na? Multiple FCU or AHU, and each FCU or AHU have its own thermostat. So in case of VRF system, number of indoor unit or number of FCU or AHU equal to number of zones. And next we have a VAV system also, that also we'll discuss. In VAV system also with one AHU you can go for multiple zones. But how, we'll discuss next. Let me complete this part first. Okay. Now the question is how to decide this zoning. How you'll decide the zoning? Whether 2 zone is required, 3 zone is required, 1 zone is enough. Not exactly. If you talk about this machine capacity or heat load calculation, that is optional in case if that much capacity unit is not available. But remember, the zoning is based on the client requirement or the application requirement. The client asks you to go for, suppose for example, this 4 spaces timing and temperature is same, we can connect with 1 unit. These 2 spaces timing and temperature is different, we'll connect with a different unit. Okay, so as per the client requirement or application requirement, you can decide the zoning. Application means say office, and in office, assume that all the suppose a office in complete 1 floor, and you got the information from the client that all the spaces, the timing and the temperature requirement is same. So based on that, we can go for only 1 AHO if the capacity, that much capacity is available to connect to all the spaces, because only one zone is required. For example, a school, all the classroom timing and temperature is same, so we can connect all the classroom with 1 unit. But the admin area timing is different, so admin area you can consider a separate unit. So based on the application, right?
Yes, sir.
So you can discuss with the client, because the client may not aware of this. So you can suggest based on the application, you get the information, what will the timing and temperature requirement for different spaces. According to that, you can decide. You see, what I explained is related to the CAV system. In VAV system, with 1 AHU, you can expect multiple zones. How I'll show you the next topic. Okay, so these are default in the market, the CAV system. CAV system means 1 unit means one zone only, whatever the number of spaces. In case of CAV system. Okay, VAV, this is also interesting. This is also very interesting and important as per the market. And if you're dealing with a big project, then VAV is a good option. Or if you want multiple zones, in that case also, VAV is a good option. So what is exactly? In short, we used to call VAV. It's a variable air volume, constant temperature system. You see, variable air volume, constant temperature system. First, let me give you the idea, the concept. For example, I'll give you a simple example. If you take a bucket of water, the cold water, suppose in the bucket, say cold water. And now, for example, assume that in winter season, the electrical water heater in your bathroom is not working. So to get the hot water, will manage through the LPG stove. No? That hot water we are going to mix in the cold water. So assume that here a container on the stove, and we are making it suppose 100 degrees boiling centigrade, means constant temperature water, the hot constant temperature water. This I am going to mix in the cold water. Initially I'll mix half and I'll check the temperature. If it is okay, I'll start to take the bath. If not, further I'll add, right? So what I'm doing here, by adding the constant temperature water, means the hot water, constant temperature water in the cold water to get the required temperature, right? Similarly, in VAV system, the supply air from the unit is constant, and by increasing or decreasing the volume of constant temperature air, we are trying to maintain the required temperature in the space. You see, once again, in VAV system, from the unit, we are supplying the constant temperature air, say 18 degrees centigrade. But in the room, we are interested to maintain 25 degrees centigrade. So how it can be done? By increasing or decreasing the volume of that constant temperature air. Suppose if I want 18 degrees centigrade in the room, the volume of air from that unit, I'm making it full, like with a valve, actually with a VAV box. But for example, for learning at this level, consider a valve. So with the valve in the pipe, by adjusting the valve, we can increase or decrease the flow of water. No? Similarly, the VAV box is used to modulate the flow of air, or increasing or decreasing the volume as per the room temperature requirement. Getting the idea? It means in VAV system, by increasing or decreasing the constant temperature air, we are trying to achieve the required temperature in the space. Okay, the concept. Now I'll open one line diagram. If you try to read this, you'll get the idea. Try to read this drawing online. It's a plan view, right? In the plan view, you can find this black color is a AHU, cyan is a duct, blue is a VE box, gray is a diffuser. With this reference, try to read this and find the difference between the CAV and VV. So the first difference here, you see this AHU with VFD drive, variable frequency drive. You know what is VFD drive? Already explained in chapter 5 at the time of VRF or VRV system, right? And the VFD drive is applicable for the compressor, fan motor, and also for pumps, which you'll find in model 3 at the time of pump selection. So VFD drive means by default this is VSD, na? Variable speed drive, and variable frequency drive means by default it is variable speed drive, and as the speed increase or decrease, the power consumption also vary, right?
Yes, sir.
The first difference compared with the CAV AHU. So in the VAV AHU, we'll find VFD drive fan motor. It means it is VSD. It can increase or decrease the speed, the motor speed, and speed is directly proportional to the flow, right? As the flow rate increases, as the speed increases, means RPM increases, the flow rate increases, right? The second difference is inside the duct, you'll find a static pressure transducer or duct static pressure transducer, nothing but a sensor which is used to measure the pressure inside the duct and continuously monitor the pressure. Here an example is given here. You'll find on different location and provide the information to this AHU or to the control system, and so that the control system can operate the speed of the fan motor. Why we'll discuss why. But the second, you see the second difference is this static pressure sensor, nothing but a pressure sensor which will monitor the pressure inside and give the feedback to the control system, so that the control system can increase or decrease the speed of the fan motor. Increasing or decreasing the speed of the fan motor means varying the flow rate. Okay, second difference. Third difference is, you see, in case of CAV, duct will directly connect with the branch to the diffuser, but in this case, in between, a VE box. VE box, for learning point of view, you can consider like a valve in the pipe. Suppose the water is flowing. With the valve, we can adjust the flow, na? We can modulate the flow. So here VE box, this VE box to modulate the flow of air. How exactly the VE box? I'll show you. So this is the third difference. Okay, so let me show you the image for the VE box. You see here one example of VE box. Inside you'll find the disc, and to this shaft we'll connect the actuator, means the motors. I'll show you. First of all, inside image. Can you find the disc inside the VAV online? You see this disc with the shaft, and this shaft will connect to the motors, modulators here, this one, and this having link with the room thermostat. Okay, so how the system works? Very simple. Assume that this is office floor, cabin 1, cabin 2, cabin 3, cabin 4, etc. Assume that the office timing is 9 a.m. starting is 9 a.m. Suppose cabin 1, some additional, he want to complete some additional work or overtime, so he visit at 8 a.m. only in the morning, and he switch on. Suppose you see this we have a thermostat in the room only, and using the thermostat he will switch on this unit. So what will happen? The H will start with the minimum speed to supply the air only to this VAV, because this VAV is on. This VAV will open and give the signal with the control system to the AHU, and the AHU will start with the limited speed to maintain the required CFM for this area. At what temperature? Say 18 degrees centigrade, because constant CAV is VAV is a variable air volume, constant temperature system, na? So temperature of air is constant, say 18 degrees. But you see the user set say 25 degree in the space. So what will happen? And the room temperature initially say 30 degrees centigrade, for example. So this 30 degrees centigrade will sense by the room thermostat and give the signal to VAV. And initially VAV will open the disc fully and supply the complete air with 18 degrees. And what happens? Supplying the 18 degrees with the full opening will start decreasing from 30 to 29 29 to 28, 28 to 27, then 26, then 25. So as the temperature decreases, you see continuously this room thermostat will monitor the room temperature and give the signal to this VAV, and the VAV have the actuators now. So slowly what will happen, as the temperature is maintaining in the space, slowly it will adjust and it will start closing. From 30 to 29, it will close slightly, then 28, 27, suppose temperature is attained, 25, what you said. At 25, it will set to minimum. Getting a point? When it's set to minimum, okay, this is one case. Now assume that at 9 a.m., this cabin 2 and cabin 2 also switch on, because the timing is 9 a.m. Now, so what will happen inside the duct when they switch on? Inside the duct, the pressure drops na, because this AH is supplying the air only for this VAV1. But VAV2 and 3, if you switch on, the pressure in the duct will drop, and we have a pressure sensor. The pressure sensor will sense there is a decrease in pressure, give the signal to the control system. The control system will increase the fan motor speed to increase the CFM to maintain the required flow to this spaces also. And the same case happen in this spaces also. As the temperature increases, this will also set to minimum. Okay, now assume that all the VAV is working now. Suppose at 9:30 p.m. means all the cabin is on, so all VAV is working. So AHU run at full load, for example, and as the temperature is maintaining, it will set to minimum. Then according to that, you see, as it's set to minimum, or suppose one cabin switch off, so it will close, or it's set to minimum. So what will happen inside the duct? The pressure increases. Again, the sensor is continuously monitoring the pressure. As the pressure increases, it will give the signal to the control system. The control system will decrease the fan motor speed to maintain the required flow rate, right? And decreasing or increasing the speed, decreasing the power frequency, and decreasing the power consumption. It means there is no wastage of energy in this. Got the concept online?
Yes, sir.
How the system works? So now the point is, here AHU is only one. So what will be the number of zones? Number of zone, remember, in VAV system equal to number of VAV box. Number of zone equal to number of VAV box, but AHU is one. Whatever the number of AHU, but the number of zone in VAV is equal to number of zones. So here 12 zones, right?
Yes, sir.
But you see, for this 2 spaces, 1 VAV, so 2 spaces, 1 zone, as per the timing and temperature requirement. And for 3 spaces, only 1 zone. So you see, this VAV, this VAV is for 3 spaces. So 3 spaces, 1 zone. Okay, again as per the requirement. So got the idea. In case of CAV, number of AHU equal to number of zone. In case of VAV, number of VAV box equal to number of zones, because each VAV have its own thermostat. Clear online?
Yes, sir.
I'll play one small animated video. Still, if you have any confusion, you'll get the clear idea with that animated video. Okay. And in that animated video, first you'll get about this HVAC system. Okay. The next part related to VAV. And HVAC system already explained at the time of chapter 5. Here, one more time revision. And in this animated video, you'll find the chiller as well as boiler, and all the AHU components, etc. So let me play this.
Refer to the system shown. There are 3 main sections involved in this system. They are cooling system, heating system, air handling unit, AHU. The cooling system is used to reduce the temperature of the environment that the HVAC system is controlling. The components of the system are chiller, cooling tower, condenser pump, primary pump, secondary pump. Let us move on to the heating system. This system is used to increase the temperature of the environment that the HVAC system is controlling. The components of the heating system are boiler, primary pump, secondary pump. The third section is the air handling unit. The AHU controls the ventilation and temperature in a building by controlling the airflow capacity. The components of this section are cooling coil, heating coil, air filter, ductwork, supply fan, return fan, inlet damper, exhaust damper, return damper. Let us now see how cooling is provided by this system. The warm water rejected by the chiller is sent to the cooling tower through the condenser pump and cooled. This cooled water in the cooling tower basin is pumped onto the chiller. The secondary pump pumps the chilled water from the chiller to the cooling coils. Fresh air blows in from the inlet damper. This air flows across the cooling coils and its temperature is reduced. The water in the cooling coil takes up the heat from the fresh air blown through it, and this warmed water is sent back to the chiller by pump for chilling. The chill air flowing out of the cooling coils is moved into the ductwork by means of a supply fan. Through the ductwork, chilled air is distributed to the individual zones. The warm air in the zones are sent back through the return fan. A part of this air is sent out as exhaust. The other part is fed back into the system through return dampers to be used for cooling. In case the process is that of heating, the hot water from the boiler is fed to the heating coil by means of the secondary pump. The water passes through the coil, and it is returned to the boiler. The rest of the flow is same as in the case of cooling. Let's start with the first module.
This part for the VAV.
By the end of this module, you will have a basic understanding on VAV application, how it works traditionally, and DANFOS solution. The key benefits of using a VLT, HVAC drive, in VAV systems. Let me begin by explaining a VAV system to you. Central Variable Air Volume System is a variable air handling system. A central variable air volume system controls the ventilation and temperature in a building by controlling the air handling unit's airflow. That is, the chilled air is distributed to the spaces from an air handling unit, and the temperature of the individual spaces are controlled by throttling the quantity of airflow into each space. But how is this done? Let us refer to the system shown. VAV systems typically bring outside air into air handling units and mix with return air, where the air temperature and humidity can be adjusted. Central fans blow the air across cooling and heating coils into ductwork, which distributes the air throughout the building to all the individual zones. The air passes into each zone from the ductwork through individual VAV boxes. A temperature sensor, located in each zone, modulates the VAV box damper to maintain a temperature set point. The system is designed to maintain constant static pressure in the supply duct and a positive building static pressure by regulating the airflow of the supply and return fans. The static pressure sensor in the ducts transmits a change in pressure to the discharge damper, or inlet guide vanes, through a controller, and the fan capacity is varied to maintain constant static pressure. The fan speed remains constant. Central VAV systems are considered to be the most energy-efficient method to air-condition buildings, because reducing air volume saves both fan motor energy and energy involved in heating or cooling air. Now that you have had an overview of VAV systems,
So I think you got the idea online. Next, so this is about a VAV system. Now we'll talk about dual duct, one more. Not commonly used, but this also one system related to air side. The topic is dual duct. Okay, but before this, some advantage and disadvantage of this VAV. Here you see advantage of VAV: low operating cost. Means there is no waste of energy, as per the requirement. Low capital cost. Capital cost compared with the dual duct, not with the CAV. Compared to CAV, the initial cost is more. Next, individual space control and simple operation, and centralized equipment, central type of AC. Disadvantage, you see all the three disadvantage at what you see: reduce air movements at reduced loads, reduce ventilation capacity at low loads, reduce dehumidification capacity at low loads, and all this disadvantage at reduced loads only. It means, for example, if you design a classroom for 20 people for peak summer, and now assume that only 5 students in the class and the starting summer. So the VAV will set the required temperature and set to minimum for longer time now, because load is less, right? In that case, what will happen? The movement of air reduces. If the movement of air reduces, that causes discomfort, and the pressure also reduces, and the movement of reduces means the dehumidification capacity also reduces. So these are the disadvantage for the VAV, but don't worry, we have some additional attachments. Using that attachment, we can overcome this disadvantages. And what are those advantages? We'll discuss in your project at the time of types of VAV box. What we learn, the VAV box is a normal type. You see, this VAV is a default type VAV box, but you'll find different types of VAV, and the types of VAV I'll explain with your school project, because in the school project we are using a special type of VAV, and at the time I'll explain the different types of VAV, not now. So, and using that additional attachment, one can overcome this disadvantage. Okay. Next we have a dual duct. So the name will give you some idea. Very simple concept. Dual duct means two ducts, right? One is to supply the cool air and one is to supply the hot air. Starting with the return air from the spaces. Some air is going to exhaust. Equal to what? Equal to fresh air. Say, for example, as per thumb rule, say 30%. 30% exhaust, so 30% fresh air. Okay. For example, as per thumb rule, you know about this ventilation. We discussed in detail about the ventilation standard. So how much fresh air, that much is going to exhaust. And the return air, the fresh air. This is mixing chamber. Mixing chamber. Here's a filter. Then suction of air with the fan, and the air is going to supply the air on the heating coil and on the cooling coil. So you'll get the hot air, you'll get the cool air. And this duct is not connected. If it is connected with insulation, okay, or I'll consider a separate duct with some distance. So here hot air in this duct, cool air in this duct, this branch for cool air, this branch for hot air. You see this branch is running backside of this duct. Okay, this one. It's not mixing here. This branch is running backside of this hot air duct. So hot air and cool air, both is going to supply to the zone or to space with a mixing damper. Mixing damper like a VV box. In VV box we have modulating this similarly mixing damper. So this mixing damper have connection with the room thermostat. Suppose in the room, if I set say 27 degrees centigrade, according to that, the hot air and cool air mix, and the required temperature air will supply to the space. Okay, simple concept. And the main ducts will continue again with the main duct, one branch for cold, one branch for hot. Again, both will supply to a space and completely return back to the unit. Okay, so simple concept. Now, if you talk about the advantage of this, the major advantage for this system is quick response in temperature. Quick response in temperature means this is generally for process control. For human comfort, we don't require 1 hour hot air, 1 hour cool air. No? As per the season, we require cool air or hot air. But for process control, consider a machine process. Starting, we require say 32 degrees centigrade. And as per the process, after say 15 minutes or 1 hour, we required say 22 degrees centigrade. So this can be achieved with the system because both the air is available. The required temperature can attain just with the mixing as per when you set in the thermostat. Quickly you'll get the required temperature in the space because both the air is available, right? So the major advantage in this is quick response in temperature. But we have list of disadvantage also. And this is commonly used for process control, not for human comfort, for process. So here you see advantages. Individual temperature control means in this also you can expect multiple zoning. Number of mixing damper equal to number of zones. Rapid temperature response. This is a major advantage. Centralized equipment, simple operation and control. But disadvantage, here you see, initial cost is more because we require a separate system for cool air, separate system for hot air, and we require large space requirement also to run a separate hot air duct, separate cool air duct, large space requirement. And energy consumption, running cost also increases because if you call only for cool air, the hot energy will waste. If you call only for hot air, the cool energy will waste. Okay, but as per the requirement for process control, we can use this. So these are the different systems related to all air conditioning system.